Today we're going to look at Chapter 16, Solubility in Complex Ion Equilibrium, and review some problems that are in the review document. I picked out a few highlighted ones. If you have any that are particularly troublesome, then we'll get to those first. Otherwise, I'll just carry on. Let's see. First one I want to look at is number 5. Barium carbonate has a measured solubility of 4.03 times 10 to the minus 5 at 25 degrees. We want to know what is the KSP, the solubility product for this particular compound. First thing I want to do is get the compound correctly written. Here's barium, and it's in an ionic compound, so it has to have a 2+ charge because it's an alkaline earth. And then carbonate is a polyatomic with a 2-. So we only need one of each. That's the correct formula for barium carbonate. This is a solid, and it's going to go into solution partially and produce barium ions and carbonate ions. There we go. Okay, if we're looking for the KSP, the solubility product says is just the barium ions times the carbonate ions to the first power, because their coefficients are 1 and 1. And that's our question. We don't know what that is yet. What we want to do is work from the value that they gave us for solubility. So if we set up our ice table and we say if so much, well, initially we got nothing here and nothing here, but we're going to have some of it go into solution. 4.03 times 10 to the minus 5 molar. Okay, so that's going into solution. That's the change from here. So that means if this much disappears from this side, it shows up on this side as times 10 to the minus 5. And also, right? So at equilibrium, we're going to have just this much molar. Okay, that means that we have values that we can place right in here at equilibrium. And we have 4.03 times 10 to the minus 5 times the same number, so that's squared. And so all we have to do is square that number and we got our answer. All right. 1.62 times 10 to the minus 9 should be the KSP. All right. That was a fairly simple one. Let's see. Let's scroll down number 6. The correct mathematical expression for finding the molar solubility of 10,2 hydroxide is. All right, so if we're given the compound, but we don't have to figure that one out. And it's going to produce one of these and 2 of these. Yeah. Okay. So I'm not going to put the ice table up here. You can if you want. But we know that well, maybe I better. Since we're talking about solubility and we'll do at least one this way. So initially we have nothing here, and we're going to lose a certain amount here, right? That represents the solubility. Actually, 2s, right? We lose one of these, we're going to get two of those. And then we have this and this to go into our expression for right, molar solubility. In terms of KSP, then we should have S to the first power and 2S to the second power, the coefficient of hydroxide. So that's going to be 4s squared, 4s cubed. Okay? And we can find the solubility. All we need is the KSP. Then we can find the solubility. Let's see, number 11. Okay. Which of the following compounds has the lowest solubility in molarity in water? The lowest solubility. All right. If each one of these compounds produced the same number of ions in solution, then we could compare the KSPs directly because they would all be represented by the same KSP and the solubilities would be built in the same way. But it looks like we have differences and we're going to have to calculate each solubility. So that means what we've got going for us is Henry Ford. Set up an assembly line. And I'm going to put the compounds here first. OH2, DS, calcium sulfate, and aluminum hydroxide. Okay. These two are going to be similar. 3, 4, 3, 4. These two are going to be similar. And this one's going to be different. So if we know the solubility, maybe I better, this first one, I should be just do it all the way to the bitter end. So you'll see where all the factors are coming from. Producing 3 silvers. I'm going to leave out the aqueous just for space. And PO4 3 minus. This one's going to produce, like it did before in our previous problem. And cadmium 2 plus and sulfur 2 minus, calcium 2 plus and sulfate 2 minus, and then aluminum 3 plus and 3 hydroxyls. Okay. So if we say that the solubility is S, then how many are we going to get over here? We're going to get 3 S's, right? And 1 S. Over here, we're going to get 1 S and 2 S's. Here we're going to get an S and an S. Here we're going to get an S and an S. Here we're going to get an S and a 3S. Okay? We okay with that? Yeah, I kind of skipped the ice table to save space. Okay, so with the KSPs of, let me put the KSPs up here. All right, first one is 1.8 times 10 to the minus 18. 3 times 10 to the minus 27. 1 times 10 to the minus 28. 6.1 times 10 to the minus 5. And 2 times 10 to the minus 33. Okay. So this expression is going to be S times 3S cubed. Because of that. This one is going to be, let's see, we did 4S cubed before. And this one is going to be S squared. S times S, S times S. And this one's going to be the same as that one. This would be 27 S to the fourth. And this would also be 27 S to the fourth. It's the same arrangement. Okay. So now all we have to do is solve those equations for S. See what the values are. All right, this is going to have to be divided by 27 and then take the fourth root. 10 divided by 27. And then the fourth root for me would be, well, my calculator is to the 0.25 power. And let's see, here it is. All right, so that's 1.6 solubility equals 1.6 times 10 to the minus 5 molar. Okay, everybody see what I did there? Your calculator may have a root button on it, or you could just put in 4 and hit the root button. Mine doesn't do that, so I have to convert it to instead of a fourth root, I have to put it to the 0.25 power. Does yours have a key like that? Let me see. I'm just curious. Let's see. Oh, well, let's see first. There's square root. Ah, here it is. There's your root button right there. That little one right there. So you have to put your X in as 4 and then get the root button. Okay. This one, let's see. Did we calculate that before? I can't remember. No, we just did the generic. So I need to divide this 3 exponent. And there, divide that by 4. And then take the third root, which would, for me, would be 0.333. And hit the power button, which would be S equals 9.3 times 10 to the minus 10 molar. Okay, this would just simply be the square root of 1 to the minus 28. And this would be 1 times 10 to the minus 14. I should have done that one in my head. And then this one is also going to be the square root of 6.1 exponent square root. And this would be S equals 7.8 times 10 to the minus 3. And then the last one, 2 exponent negative 33. And divide by 27. And then take the fourth root. Let's see, there it is. And this is 2.9 times 10 to the minus 9 molar. Okay, so we got these for comparison. There we go. And the question was, which has the lowest solubility? So the smallest number, I always look at the powers first. If there's a -9, 3, -14, this is it right here. That's the lowest solubility. We didn't even have to look at the coefficients. We just check out the powers. See, that was -14. Okay, that's a lot of work to answer a simple question, but if you set it up like my assembly line procedure, then it should go a lot quicker. Okay. Let's see, where was I? Number 13 coming up. All right. The molar solubility of barium carbonate in 0.1 molar barium chloride solution is. All right. First question is, what does barium carbonate do in solution? Barium carbonate breaks up into one barium and one carbonate. Okay. And now we're going to, and the KSP, let's get that up there, is 1.6 10 to the -9, which is equal to barium and carbonate. Here we go. But we're not in water. So that means we're starting off with an initial value here for these. Which one of those? Well, which one's the common ion? Barium chloride is completely soluble. It's 0.1 molar. So if barium chloride goes into solution, right, this aqueous solution produces barium and two chlorides. Right? Does it matter what the chlorides do? No. No, because the only thing in there is barium and carbonate, and chloride and carbonate don't interact. They're maybe competing for bariums, but the barium chloride is completely soluble. So whatever this concentration is, 0.1 molar, that's also the concentration here for that barium. So that means we're starting off with an initial concentration of, is that right? 0.1? Yeah, 0.1 molar barium and no carbonate. So what that also tells us is we're still going to get some this is still going to solubilize to a small extent because we don't have any carbonate in solution yet. Right. So Le Chatelier says it's going to move this way because that's 0. So we are going to lose some here. It's going to show up over here. Oops. Try that again. Plus S and plus S. Right. So we have 0.1 plus S and S. Then we can substitute values in here. So we're going to have 0.10 plus S and then S. Okay. Now let's see, we're going to have a quadratic problem here. Yeah, we're going to have S squared and we're going to have an S term, right? With our X squared and we're going to have an X term. So it may be useful to approximate. Now this is very low solubility to begin with. So you can imagine if we already have some barium in there, we're going to get even less. So we should be able to say that S is significantly smaller than this value, which means we can estimate it as 0.10 times S. That's a whole lot easier to solve the problem. So if this is equal to that, then 0.1 in the numerator here is in the denominator there. So we would say 1.6 times 10 to the minus 9 divided by 0.10 equals S. So dividing by 10 to the minus 1 is the same as adding. So it should be 1.6 times 10 to the minus 8 molar. Oops, I went the wrong direction, didn't I? No, none of these. Right. That's right. We just, it's just, so we did barium carbonate earlier, right? Let's see what it was in pure water. Barium carbonate in pure water. Here it is 1.6 10 to the minus 9. Right, so it's an order of magnitude. Wait a minute. It should be less soluble. Okay, I did something wrong here. Hold on. Let's do it the long way. I thought I could do it in my head. Oh, that's right. 1.6 times 10 to the minus 8 molar. Oh, wait a minute. Barium carbonate. Oh, wait a minute. That's the solubility. I'm sorry. KSP. This is solubility. 4.03 times 10 to the minus 5 is the solubility of carbonate in pure water. Right? So there we go. We're about 3 orders of magnitude less soluble. Okay. Did I confuse anybody? I was looking at the wrong numbers. The answer to that problem is the KSP, which we're given right here. What we want to compare is this value with the given value of 4.03 times 10 to the minus 5. So it is significantly less soluble because we have that barium common ion in there already. Okay, that's 13. Now we can go down to 17. It's kind of weak. Go. Which of the following solid salts is more soluble in 1 molar hydrogen ions than in pure water? Okay. Notice it doesn't say what type of acid that is. We're only focusing on the hydrogen ions that are delivered by acid. More than likely, it's going to be a nitric acid so that we don't precipitate some of these compounds. Okay, which is going to be more soluble in 1 molar hydrogen ions? Right. So we got A, B, C, D, and E. And our choices are sodium chloride, calcium carbonate, potassium chloride, silver chloride, and potassium nitrate. Well, we can throw potassium nitrate out because it's completely soluble regardless of what we put in there. Right? This is completely soluble, so we can throw that one out. Notice that this is a chloride, chloride, and chloride. If we put this in solution, each one of these in solution, then we have some silver here, some chloride there. We have some potassium here, some chloride there. and some sodium here, and some chloride there. Now you can reach saturation with these two, sodium chloride and potassium chloride. But adding acid, how would acid, let's see. Yeah. How would acid affect their solubility? Well, it wouldn't, because it's not it doesn't react with any of these, right? If we have H plus in here, right? H plus and chloride, it's completely soluble. Hydrochloric acid is completely soluble. So it's not going to affect the concentration of either of these. That makes sense? Okay. But for this one, carbonate, if we add hydrogen ions here, they're going to react with this one and produce that. Remember when we did acid equilibrium, we had H2CO3 in equilibrium with H plus and HCO3 minus, and then we had HCO3 minus. The next one, CO3, 2 minus. Well, the acid ionization constants for each one of these is very small. Let's see. Actually, what it's going to do is when we add acid to this, it's going to take this one to that one, and then more of it's going to go back to this one. So we're going to end up right here. So we're actually removing carbonate from this side and increasing the solubility of carbonate, calcium carbonate. That's all you need to know to answer the question. But as a matter of course, this is very unstable. So what it's going to do is go back to actually two waters and CO2. Actually, one water, excuse me, one water. So that's why when you add acid to calcium carbonate, you get gas. Right? When you eat a Tums with a sour stomach, you're probably going to belch because it's producing this gas in your stomach. But the point is, what this acid does is it reacts with the carbonate. This is a strong base, a Lowry-Bronsted base, strong base, which means it's looking for hydrogen ions, and it's going to find them right here. When it does, it removes carbonate from this part of the equation and drives the reaction to the right. So that whenever you have a strong base as a product of solubility, adding an acid will effectively make it more soluble. That's what's required, that strong base. Okay? All right. Number 19. And that's already gone. Another one. Okay. You have a solution consisting of 0.1 molar chloride, 0.1 molar chromate. You add 0.1 molar silver nitrate dropwise to this solution. Given that the KSP for silver chromate is 10 to the minus 12 and for chloride is 10 to the minus 10, which of the following will precipitate first? All right, what we have to do, see, we can't compare the solubilities of the silver compounds directly because chromate snaps up two silvers and chloride only snaps up one. So we have to compare their solubilities like we did before. All right. So chromate ions, let's see, silver chromate. Silver chromate is going to yield. Actually, we're running the reaction backwards, but we need to do this calculation in order to answer the question. Okay. The other one is silver chloride. Okay. And we're adding silver dropwise. Silver nitrate, the nitrate is a spectator. The silver plus one ion is what we're adding here. So, which one becomes soluble first? Well, let's see. If we have KSP for silver chromate is 9 times 10 to the minus 12. 9 times 10 to the minus 12, which would be equal to, this would be 2S, right? This is S. This would be 2S. This would be S. And if this is S, this would be 1S, and this would be 1S. Right. So this is going to be equal to 2S squared times S. And this one, 1.6 10 to the minus 10, 1.6 times 10 to the minus 10 equals S squared. Okay. So we can calculate the solubilities and see which one is more soluble. Which one is actually the least soluble one is the one that's going to precipitate first. Okay. So we do a quick calculation here. So we did that one already. 1.6 exponent 10 and take the square root. This solubility is 1.3 times 10 to the minus 5 molar. And this one is 4S cubed. So we'll divide 9 exponent 12, divide it by 4, and then take the third root. This is 1.3 times 10 to the minus 4 molar. I did that right. Did I do that right? 4S. Yeah. Okay. Let me do it one more time just to be sure I punched in the numbers right. 4. Yeah. And that's 4. Okay. Okay. So which of the following will precipitate first? Well, the one that's least soluble, right? 10 to the minus 5 versus 10 to the minus 4. This one's going to precipitate first. So if add dropwise, you need to know something about the stoichiometry to know when to stop and filter out silver chloride. If you want to separate the chloride from the chromate. Okay. 21. I don't know if I did it that way in the worked problems, but it worked this time. Let's see, 21. Oops. These old ones are only good for one time. Okay, how many moles of calcium nitrate must be added to 1 liter of 0.182 molar potassium fluoride solution to begin precipitation of calcium fluoride? For calcium fluoride, the KSP is 4 times 10 to the minus 12. Okay, I put a hint in there. We're looking for at what point, at what calcium concentration does the Q equal to the KSP? All right, so we want to precipitate calcium fluoride. Which would solubilize as this and 2 of these. Okay. So it's KSP is equal to what? 4 times 10 to the minus 11. And that's equal to that's equal to calcium ions and fluoride squared. Okay, so we know that the Q is going to be equal to this value. If we had a Q, then we'd have calcium like that and fluoride like that. And we want to calculate what the Q is. So what is the Q? Well, let's see. If we're adding calcium nitrate to 1 liter, that's molarity. 0.182 molar fluoride. So we have 0.182 molar fluoride right here. 0.182 molar fluoride squared. And then we have calcium here, right? And then we can calculate what that Q is and compare it to the KSP. 0.182 and then square it. Oops, try that again. There we go. This is 3.31 times 10 to the minus 2. And that's equal to 4 times 10 to the minus 11. So calcium then is going to be this one divided by that one. Let me make that plain. 2, there we go. Divide that into 4 minus 11. Let that divide. Okay, so the calcium concentration would have to be 1.21 times 10 to the minus 9 molar. And if we put that in liters, then this would also be moles. This is moles per liter. Multiply it by 1, you get 1.2 times 10 to the minus 9. That's how many moles of calcium ions have to be in solution to begin precipitation of calcium fluoride. Okay. If it doesn't make sense, we'll try it a different way. But I think that's the simplest way to solve the problem. You begin precipitation when KSP and Q are equal. All we need is just a is just a hair more. And well, actually a hair more than this. And we start precipitation. All right. It's down on me. That one. 23. All right. A solution is 0.1 molar in each. Lead 2 plus, manganese 2 plus, and zinc 2 plus. Sodium hydroxide is added until the pH of the solution is 8.5. Which of the following statements is true? No precipitator form. Lead 2 hydroxide will precipitate, manganese 2 hydroxide, or zinc and lead will precipitate. All three will precipitate. Okay. So if we're going to determine precipitation, we need a Q value that's equal to or exceeds KSP for one or more of those. Right? If we're going to have, let's put our equations up here. Lead 2 hydroxide is going to give us lead 2 plus and hydroxide. That the second one, manganese 2 hydroxide. You know, I may be overthinking this one. Because each one of these is going to produce the same equation for precipitation. Because you've got the same number of each components. Okay. So that's given. Let's see. We have 0.1 molar in each of these. So we're starting off with 0.1 molar of each of these right here. 0.1 molar. Right? What we want is what is this concentration? Right? So that we can calculate the Q for each one. All right, so the Q for this one is going to be lead 2 plus. Well, let's just put the value in there. They're all going to be the same. 0.10 times hydroxide squared. This Q is going to be 0.10 also. Yeah. And let's see, the KSPs for each one are 10 to the minus 20. 1.4 times 10 to the minus 20. 2 times 10 to the minus 13. And 2.1 times 10 to the minus 16. 2.1 times 10 to the minus 16. Okay, so how do we calculate the hydroxides? We add sodium hydroxide to the solution until we reach pH 8.5. Right, we know the pH is 8.5. Right? And we can calculate the hydroxide concentration. Remember that? So what's the POH? POH is 14 minus 8.5. which is, let's see, 13 is 5.50. So the OH concentration equals 10 to the minus 5.50. Remember that? From chapter 14. Okay. So we just take the anti-log of minus 5.5. 5.5, change the sign and go 10 to the x. That's 3.16 times 10 to the minus 6 molar. Okay. So really all we have to do is calculate that once. 3.16 times 10 to the minus 6 squared times 0.1 is the Q. Let's see, I already got that one in my calculator. I'm going to square it. And then times 0.1. And I get 1 times 10 to the minus 12. All right. So we compare that value to the KSPs. Right? That Q is greater than this KSP. So lead hydroxide will precipitate. 10 to the minus 12 is greater than 10 to the minus 13, isn't it? Let's see. Is that right? Wait a minute, that says that all of them are going to precipitate. Did I write the right numbers up there? Minus 20, minus 13, minus 6, 20, 13, 16. .5, change the sign, do that. That's right. And this has to be squared. 3.16 exponent squared. Oh, I got a different number. 9.99. Okay. 10 to the minus 12. The Q is greater. This one. Oh. 10 to the minus 12 is greater than 10 to the minus 20. Greater than 10 to the minus 16. Greater than 10 to the minus 13. So they all should precipitate. Let me look at my work problems. Why do I have D as the answer? Yeah. 23. See if I made a mistake. Hydroxides, 3.16. Yep, that's right. Calculate the okay. Q is 10 to the minus. Oh, that's my mistake. Let's do that again. 3.16 exponent minus 6 squared 0.1 times 13. There's my bow. There's my boo-boo. Okay, so that one is still bigger than this one. It's bigger than this one, but it's it's 14. Oh. To the minus 14. Wait a minute. square it. Okay. And 0.1 times. That's right. 10 to the minus 13. Right? Do you get the same thing? 10 to the minus 13. Okay. So if that's 10 to the minus 13, 9.99, 10 to the minus 13. If the Q is greater than the KSP, we're going to get a precipitate. So it should be all of them. Now, how did I end up with this says 10 to the minus 14. I think I made a math error. I'm going to do it one more time. 9.9, 3.16, 10 to the minus 6. Yes, that has to be squared. Nine point nine nine times 10 minus 12, and then times 0.1. Yeah. That's 10 to the minus 13. So this is wrong. It's 10 to the minus 13. And all of them. Okay. All of them precipitate. So that answer should be E. Correct? Yeah. Yeah. Okay. Now that one got away from me for so many years. Oh, no. I made a double boo-boo. You see what I did? Okay. I'll put the math back up here. It was right the first time. And here's why. pH 8.50, pOH 5.5, hydroxide ion concentration 10 to the minus 5.50 equals 3.16 times 10 to the minus 6. Okay, so Q is equal to 0.01. Okay, that was my big mistake. 10 to the minus 6 squared. So Q equals 9.99, 10 to the minus 14. Okay, so for lead hydroxide, manganese hydroxide, and zinc hydroxide. This one, the Q is greater than the K. This one, the Q is greater than the K. And this one, the Q is less than. Okay. Okay. So these two are the only ones that precipitate. So the answer is still D. Okay. That was my big boo-boo. I was using 0.1 and the problem says 0.01. So that changed the comparison of the Qs and the KSPs. So the problem is correctly worked in the work problems. I just messed up. Okay, next. Okay, 24. In the qualitative analysis scheme for metal ions, how are the analytical group 2 cations separated from the cations of analytical groups 3 through 5? For that one, all you have to do is go down to the useful information. All right, here we are. How do we separate 2 from 3 through 5? In an acidic solution, we add hydrogen sulfide. So by addition of H2S in acidic solution, forming insoluble sulfides. It's just that simple. All right, 25. Which of the following solid salts should be more soluble in 1 molar ammonium than in water? So this goes back to how do you get a salt into solution? An insoluble salt into solution. You have two possibilities. If the anion, say we have X and Y, this is the anion, this is the cation. If the anion is a strong base, we add hydrogen ions. Okay. If it's a weak base, then we have to attack the cation. And then for the cation, we need to form a complex ion. Okay. Which one of these can we do that with? With ammonia. Well, the only one we studied is silver. Right? Sodium, potassium, and potassium. Actually, we don't need any. Well, sodium carbonate, if we need to make it more soluble, we just add hydrogen ions. And that would put that into solution because carbonate is a strong base. But silver bromide is the one where we attack the cation to make a complex ion with ammonia. All right. Now the one we're going to do, I think in 2 weeks, is we're going to determine the formation constant of the diamino silver complex ion. Okay, 27. And we're going south too. The correct mathematical expression for finding the molar solubility of lead-2 chloride is lead-2 chloride. All right, so we're going to put it in solution with a lead 2 plus and 2 chlorides. Okay, so what we're going to end up with, I'm going to kind of abbreviate the ice table. if we're going to solubilize this, right, we're going to get one of these, and we're going to get two of those, right? So when we put it in our expression, KSP equals what? Well, the KSP is equal to the lead 2 plus term times the chloride term squared. Okay. So we did one like this earlier. It's kind of repetitive. So this is 4s cubed, which would be D. 30. Which of the following leads to the formation of precipitate? Just memorize it, right? Q is greater than KSP. Let's see. 34. Let's see. Calculate the solubility of silver chromate in a 0.049 molar silver nitrate solution. All right, let's see. Silver chromate. Is going to produce 2 silvers and 1 chromate. Right? Yeah. And we're going to calculate the solubility in that solution. All right, first of all, when silver nitrate goes into solution, what does it produce? This solution produces 0.049 molar silver and 0.049 molar nitrate. Nitrate's not common to this reaction. It will have no impact on it whatsoever. But the silver will, because we're starting off with 0.049 molar. And the change is going to be the solubility of this compound. Right? So we're going to have plus 2 S's here and just plus 1 S here. Right? So we're going to have 0.049 plus 2S and S. So the KSP is given as 9 times 10 to the minus 12. Which is equal to yeah, equal to 0.049 plus 2S. Since this is the silver term, it's going to be squared. And then we're going to have a chromate term. Right? Now, this is extremely insoluble compound. So that 2S is probably going to be so small that it's not going to impact this value. So I think we can approximate this as 0.049 squared times S. 0.049 and square it, and then divide it into this number. Yeah. S should be 3.8 times 10 to the minus 9 molar. Close enough. Now, why did I get 3.8 instead of... Oh, I rounded wrong. Sorry. Yeah, I rounded up and I shouldn't have. 3.7. That's right. 3.7. Now, if we want to be sure, Now we are within 5%, we would take this value and plug it in right here. Right? Take this value, plug it in here, and calculate that value and compare it to this one. Let's do it just for fun. So I'm going to put this value, which is S, right here and here. I'm going to take, let's see, 2 times that one and 0.049 plus, and then I'm going to square it. And then, then 3.7 times. And I get the calculated K with this value is 8.9 times 10 to the minus 12. All right, so it's 0.1. The difference is 0.1 divided by 9 times 10 to the minus, well, actually it's 0.1 divided by 9 times 100. I just left off the powers of 10. Right, that's 1%. So we're within 5%. And the estimation was a valid procedure. 36. Here, use up. How many moles of calcium fluoride will dissolve in 3 liters of 0.089 molar sodium fluoride solution? Okay. We're going to have to find out what its solubility is, and then apply the volume. All right, so if we have calcium fluoride, and it's going to make calcium 2 plus and 2 fluorides. And initially we have 0 fluoride, right? Wait a minute. No, sodium fluoride, 0.08 sodium fluoride, 0.089 molar. Sodium's a spectator, and we don't have any calcium. So the change is going to lose some of this. It's going to show up over here, and it's going to show up over here as 2. So at equilibrium, we're going to have 1s here, and we're going to have 0.089 plus 2s. So our KSP is equal to 4 times 10 to the minus 11, which is equal to, we square this one. Well, let's put the S in here. And then the second one, 0.089 plus 2s is going to be squared. And we're going to approximate that. We're going to get rid of those s's. This is going to be s times 0.089 squared. All right. So let's square this and divide it into that. Okay. So solubility is equal to 5.0 times 10 to the minus 9 molar. And they want to know how many moles of calcium fluoride will dissolve in 3 liters. So this is per 1 liter. So we need to multiply this times 3. And that's 15 times 10 to the minus 9 which is 1.5 times 10 to the minus 8 moles of calcium fluoride. 10 to the minus 9. Why did it say 8? Oh, I went the wrong direction. I didn't do it. There we go. Last one. Okay, 37. What's the best way to ensure complete precipitation of tin sulfide from a saturated H2S solution? Right. $37. If we want to solubilize tin 2 sulfide from a saturated H2S solution, best way to ensure complete precipitation. Now that's assuming that you have the tin 2 plus ion in solution and you're trying to get it out. Right. So we'll have there. 2 minus. Okay, we want to get the maximum amount of this out. So we want to maximize this anion. So how do you do that? Well, we need to be sure that this is completely soluble. We want to increase its solubility. So we go back to H2S produces 2 hydrogens plus an S2 minus. And originally, what we wanted to do was precipitate the least soluble first. So we were sure that we were acidic. We had lots of these in here, which drove the reaction back this way and gave us only a few of these. Right? So that's how we precipitated the one group, the group 1 anions as cations as sulfides. But if we want to be sure to get all of it and it's in solution, then what we want to do is produce lots of this, right? So we need hydroxides to produce water, and that will give us a lot of those sulfide ions. All right, so adding more H2S is not the trick. Add a strong base. Add a strong base like any hydroxide will do, and that will produce lots of this and precipitate all of that. Okay. Number 40. Good. Dig into my pocket now. Number 40. All right, the concentration of magnesium 2 plus in seawater is 0.052 molar. And what pH will 99% of the magnesium be precipitated as the hydroxide? All right, we're going to precipitate it as the hydroxide. There. Okay. So we've got this in solution. And we've got this. Like that. Okay. We want 99% of 0.052 molar. So if this is 0.052 molar, we only want 99% of it. So 0.99 times that will be the amount of magnesium we want to remove from that solution. 0.052 and 0.99. This is 5.15 5 times 10 to the minus 2 molar. Okay. The precipitate concentration 90% precipitated hydroxide. At what pH? Okay, so if we want to precipitate all of this, we need a stoichiometric amount of this. What's the stoichiometric amount of that will remove all of this? Right, so this is going to be that many mole, that's molar. We want a concentration here of hydroxide that will be stoichiometric to this amount. Right? So if this is 1, then we need twice that much. Like 2 times that would be our hydroxide concentration. So we need hydroxide concentration of 1.0296 times 10 to the minus 1 molar. Okay? So what's the pOH? Well, the negative log of that value, right? Take the log and change the sign. This is 9.87 pOH, and pH then would be 14 minus that. 13.01 pH. Okay. Now what did I do wrong? Oh, I didn't include KSP. Hold on a second. I'm jumping the gun. Let's see. If this is the initial concentration here, okay, I'm barking up the wrong tree. Yeah, I didn't include KSP. Yep. So what we need is not the stoichiometry. KSP equals what? 8.9 times 10 to the minus 12. 8.9 times 10 to the minus 12 is equal to what? Well, we got this concentration in there already. 5.15 times 10 to the minus 2. But this concentration is squared. Now we can find out the hydroxyls that we need. So I'm going to take that value, 8.9 and 5.15, divide, and then I want to take the square root of it since it's already in here. All right, so the hydroxide concentration needs to be 1.315 times 10 to the minus 5. Okay, pOH equals the negative log of that. 4.88, and pH equals 14 minus 9.1. 9.1 pH. Yep. I was trying to take a shortcut and it sent me to Timbuktu. Let's see, 41. How are we doing on time? 30. Okay, we'll go till 10:25. We might be shorthanded today. Hey, now why did my oh, there it is. Okay. Wait a minute. There's a chat. I missed the chat. Okay, that's fine. Back to share. There we go. 41. Okay. A solution contains 0.01 moles each of iodine, bromine, and chlorine. When the solution is mixed with 200 milliliters of 0.24 molar silver nitrate, how much silver chloride precipitates out? Here, since silver iodide, silver bromide, and silver chloride are all will produce the same results in solution in terms of their, solubility, right? You get silver ions, one silver ion each, and then one of the anions each. Like that. And we also see that the solubility is, let's see, KSPs. Let's put the KSPs out here. 1.5 times 10 to the minus 16. This one is more soluble, 10 to the minus 13. And this one is the most soluble. Just compare it, minus 10, minus 13, minus 16. So when we have 0.01 moles each of iodide, bromide, and chloride, when the solution is mixed with 200 milliliters of 0.24 molar silver nitrate, how much silver are we adding at the top? 0.24 moles times 200 mils. 0.24 molar times 200 mils. Right. So 0.24 and 200 times is 48 millimoles. Remember, molarity times milliliters is millimoles. So we're starting off with 48 millimoles. All right. How much iodine are we starting with? 0.01, 0.018 moles, or 18 millimoles. Each one has 18 millimoles of the ions, of the anion. Okay? So, this is silver, right? Yeah, this is silver. So this is the least soluble, so it's going to react, and this is limiting. It's going to run out. Right? So what do we have left here? Minus that is 30, right? 30 millimoles. 18, yeah, 30. Then we subtract 18 more from that one, and it's going to run out because there's plenty. Right? This is excess, this is limiting. So what we have left is what, 12? Yeah, 12 millimoles remain. Okay, so now which one is excess? This is excess now. So we have this much silver but this is limiting. So it's going to run out. Right. So we have, oh, wait a minute. How much silver chloride precipitates out? Oh, good. There's nothing left, but we do have 12 millimoles of silver as silver chloride. 12 millimoles. Okay. How much silver chloride precipitates? Well, this is millimoles. How many moles is that? 0.012 moles. Right. And that's silver. It's also that much silver chloride because it's 1 to 1 to 1. So this is silver chloride. Silver chloride. And we're asked the mass. Okay. Hey. So now what we need is molar mass for silver chloride. Right. Silver is 107.87. And chloride is 35.45. Right. We'll add those together. Is 143.32. Moles cancel. 0.012 is 1.7 grams of silver chloride. Okay. Okay, with the logic. Okay. There. All right, let's see, where was I? 41, let's see, 43. Okay, we got another. We have to go to the useful information to answer this one. When a mixture containing cations of analytical groups 1 through 3 is treated with acidic H2S, which cations are expected to precipitate? All right, so let's go down and acidic H2S. If we've got groups 1 through 3, 1 through 3. So we have these silver, mercury 1, and lead 2 plus. We also have this group here. So if it's acidic, well, it doesn't say that it's acidic hydrochloric, right? We have to assume that that's the step that we're doing. So we're going to take out silver, mercury 1, lead 2 plus, and I even forgot the question already. Treated with, okay, H2S in acidic conditions. We're going to take out groups 1 and 2. Right, we're going to take out the chlorides, and then we're going to take out the less soluble sulfides. All right, 46. The cation M2 plus reacts with ammonia to form a series of complex ions as follows. Okay. a 1 times 10 to the minus third mole sample of metal nitrate is added to 1 liter of 15 molar ammonia. Choose the dominant species in this solution. Okay, that's not as complicated as it looks on the surface. If you see the sequence of ammonia additions, right? Well, 1 ammonia at a time. The first one is 10 squared, so it's essentially all the way to the right. The second one takes that first cation, adds another ammonia, it's all the way to the right. And then we take that one and add another ammonia, it's all the way to the right. Right? So the dominant species, we don't need to know all that other stuff. The dominant species here is going to be the triple aminated metal, right? Which would be D, right? And that would have a K, overall K of let's see, 2, 5, 6, 7, 10 to the 7th. Yeah, so it's going all the way to the end. 47. What's the concentration of nickel 2 plus ion in 0.05 molar nickel nitrate solution that is also 1 molar ammonia? And a KF for the overall KF for the hexamino nickel ion is 5.5 times 10 to the 8th. Okay, so let's write since we're going all the way to the end, let's write the overall equation. So we're going to have nickel 2 plus, right? And then we're going to have 6 ammonias. And this is going to be in equilibrium with the complex ion. Like that. And then there's a charge. And this is, everything's in aqueous solution. And our formation constant is 5.5 times 10 to the 8th. Which is equal to the complex ion. And then we got nickel to the plus and ammonia to the 6th power. Okay, so that's what we're working with. Let's see, what's the concentration of nickel ion in solution? Okay. All right, it didn't tell us anything else except for the concentration of nickel nitrate. Okay. So initially, we have 0.045 molar nickel. And we also have 1 molar ammonia. Okay. And we're saying that initially. So the change is we're going to lose some of this, and we're going to lose 6 of these, right, to produce 1 of these at equilibrium. So this is 0.045 minus X. This is 6X, see, 1, excuse me, 1 minus 6X, and this is X. Okay? See if I got that right. Got all my numbers right. 1 molar, 0.045. Yep. Okay. So, scooch this over a little bit. 5.5 times 10 to the 8th is equal to X up here. And 0.045 minus X. And then 1 minus 6X to the 6th power. Right? Is that the way I worked it here? $47. Yeah, 47. Yeah. Okay. I did do some approximation. Hold on. All right. This is 0.055. Okay. This term is messed up. So we're starting off with 0.045 molar nickel. 1 molar here. Do we have any of that in solution? No. Now why did I do this? Oh, no, that's equilibrium. Oh, I did stoichiometry first. Sorry. Yeah, I'm getting ahead of myself. All right. Yeah, follow my own rule. So this is begin, and this is end for stoichiometry. So now what are we starting with? We're starting with nickel ion in concentration of 0.045. 0.045 of molar. Okay. Ammonia, we're starting at 1 molar and 0 here. So I'm going to use up 0.0445 molar. Yeah, 0.05 molar. So I'm going to have 0 here and 1 minus 6 times 0.045 molar here. And that's going to produce 0.05 molar there. So if we use all that up, we get over here. So this is our starting point for our equilibrium. Okay. See where I messed up? 0.730 should be this calculation. So now we're starting at 0.730 molar. Let me be sure I'm doing that right. 0.045 times 6, subtract from 1. Yeah, 0.730 is where we start here. And we start here as 0. And we start here as 0.045 molar. So that's the initial starting point for our equilibrium. Now we can build the ice table. Okay. Now the change is going to be back this way. All right, so if it's going to shift this way, that means we're going to add this much. And we're going to add that much here. Right? And we're going to subtract that much. Let me see if I'm on track. Yep. Okay, now I think I can wean the rest of the way. And these values are definitely going to change. Okay, so we're going to have X here. We're going to have 0.730 plus 6X. We're going to have 0.045 minus X. So in the numerator, we're going to have 0.045 minus X. We're going to have X here. And we're going to have 0.730 plus 6X. And then we're going to estimate. We're going to say that relative to these values, the X's are not going to be that big. So we can leave this one X. We can leave this X down here because we can't get rid of that one. Otherwise, we won't have a term there. But we can estimate this one to be 0.045, and then X, and then 0.730 to the 6th power. And that's all equal to 5.5 times 10 to the 8th. So, take the 6th power of 0.73. 16. There. I get 0.151. 0.1513. Right, times X. And then I'm going to take these over here, multiply that one times this value. And that gives me 8.32 times 10 to the 7th X equals 0.045. So I divide both sides through by this value, and that leaves X on this side. And that's 5.41 times 10 to the minus 10 molar. And X is the concentration of nickel. Okay. I don't know if I could have solved it the other way. I suppose I could have. It would have been tedious, I think. Anybody know where Augusta is? No. Does she work? I haven't graded your kinetics yet because I was waiting for her report. I guess I have to go ahead and do you guys. Get that grade in the books. 50. Let's see. The KF for the complex ion 1.7, 10 to the 7th. The KSP for silver is calculate the molar solubility of silver chloride in 1 molar ammonia. I'm going to, rather than waste your time, I'm going to refresh my memory. Okay. So for this one, we've got two equations operating. One is the solubility of silver chloride. And let's see, it's silver and chloride. And this KSP, I'm going to go ahead and write it here. It's 1.7 times 1.6 times 10 to the minus 10. Okay. We also, in the same solution at the same time, we have the formation of the complex ion. All right. Let's see. Yeah, that looks good. And this one has a KF equal to 1.7 10 to the 7th. All right. Let me see. I know I need to combine the equations. All right. However much of this goes into solution, right? If we say that's the loss of this side for the solubility, it produces this and this. So this term right here, that chloride concentration will tell us what the solubility is. So if we add these two together, the reason I say that is because the silvers are going to cancel when we add them together. So we get silver chloride, right? We add these two together. We get silver chloride. And these cancel. Plus 2 ammonias. And then we're going to get chloride ion in solution and silver diamine silver ion. And the KF is going to be the product of those two values. 0.7. Is that right? Yeah. And this is, so the K for this one is 2.72 times 10 to the minus 3. All right. So, right. Okay. So this K, I'm gonna have to write it again over here. 2.72 times 10 to the minus 3 is equal to chloride ion concentration, complex ion concentration, divided by ammonia squared, right? That's a solid, so it doesn't count. All right, so we want to find the solubility. All right, change. There we go. So what are we starting out with? ammonia concentration is 1 molar. I hope this works. Oh, 0, 0. Then the change is going to be, we're going to solubilize some of this, and it's going to produce some of that. And it's going to subtract 2 of these, minus 2 S's for that, and produce another one of these. Right? See if I'm on track. All right, so at equilibrium, this is going to be 1 minus 2S. This is going to be S. This is going to be S. So the chloride is going to be S. And this one's going to be S. This one's going to be 1 minus 2S squared. All right. Notice this term right up here is S squared. All right. So all we have to do is combine the two. Right? And this whole thing is squared. And that's equal to 2.72 times 10 to the minus 3. So if I square both sides, then I get these terms freed from that square. I mean, square root. Take the square root of both sides. Square root of this and the square root of that will get rid of the square. This is 5.22 times 10 to the minus 2 equals S over 1 minus 2S. Okay, then this has to be multiplied by that side. So this is 5.52 times 10 to the minus 2, and then minus 1.04 times 10 to the minus 1, S equals S. All right, so now we can leave this on this side, add this to both sides, and this would be, well, this is 0.104, right? So if let's bring it over here. If I add this to both sides, then that's 1 plus 0.104. 1.104 S. And that leaves 5.52 times 10 to the minus 2. And then I just divide both sides by 1.104. And S is apparently 5 times 10 to the minus 2 molar. Solubility. What was the question? Molar solubility. I get 4.7 times 10 to the minus 2. All right. Where did I go wrong? Did you catch me? 2.72. Screw to that. Okay. 10 minus 2, that's right. Minus 104, 10 minus 1. 1.104. We're good down to there. So I must have used something that was already in my calculator. Let me put them in manually. Yeah, that's it. It's a rounding error. Yeah, it's a rounding error. So this should be 4.7. times 10 to the minus 2 to match with the answers available. All right. That was a lot of work. If I were active in this area of research, now we're using the same reaction over and over again, I'd build a spreadsheet so I can just plug in the values and spit out the numbers. But we got to learn to do it manually first. Okay. 52. This one, as I recall. There she is. Everybody's been asking for you. Let's see. For a system, 500 milliliters of 0.02 molar manganese 2 nitrate is mixed with 1 liter of 1 molar sodium oxalate. The oxalate ion acts as a ligand to form a complex ion with a manganese ion with a coordination number of 2. Okay. So we're given it, well, 2 oxalates are required for the complex ion. So that's why we're given 2 equations. What's the equilibrium concentration of the first oxalate? All right. Yeah, I need to invert. Okay. So the first one is in the proper order because we're forming that very first complex ion, manganese oxalate. C2H4. Oh, not H. Oh. 2 minus yields the first one. Okay, its K is 7.9 times 10 to the third. Okay, the second one is written in the wrong order. Right? If we're looking at equilibrium, and we want to do a stoichiometric reaction and then work backwards to this value, we need to invert that equation. All right, so this is going to be, let's see, I'll put it down here. This is going to be Mn. Well, it's going to be that one. Mn, not 2. You guys are letting me get away with murder. There we go. And this is in equilibrium with, no, we need to add another oxalate. Now, Mn, and then 2 oxalates. This is 2 minus. Right? 2 of these. Okay, what's the K for this one? If you flip the equation, you also invert the K. Right, so we just need to take that K and invert it. 1.26 times 10 to the minus 2. And take the inverse. So this is, actually, I can write 79.365. Okay. I'm still gonna cheat, be sure I'm on track. Okay. So before anything happens, we've got 500 milliliters of 0.02 molar manganese nitrate. So the manganese ion to start, before anything happens, is 0.02 molar times 0.5 liters. Zero 0.5 liters. So this is 1 times 10 to the minus 2. Am I doing that right? Well, if I want to calculate all right, this is moles of manganese ion. But the concentration is that divided by the total volume. Right, we have 500 milliliters plus 1 liter. So it's 1.5 liters of total solution, because we added 1 liter of 1 molar. This is 1 molar and 1 liter. Right, so it's 1.5 liters here. Is equal to what concentration? So this is 6.67 times 10 to the minus 3 molar manganese. That's the start. Okay, the oxalate ion should be calculated by a similar procedure. So this is 1 liter times, that's 1 mole divided by 1.5. Right, so 1 mole of oxalate divided by 1.5 liters equals what? Is 0.667 molar. So this is oxalate concentration at the beginning. And this is manganese concentration at the beginning. All right? That's what we're starting with. Okay. Let's see. Do I need to combine those? Well, if we say, what are we going to end with? Okay. And with this row, I'm going to be referring to these items here. We're going to end with that. We're going to use up all of our manganese. The best way to solve these types of problems with these complex ions is to do the stoichiometry first and then work your way back to equilibrium. So we're going to end with this is going to be all used up because that's only 10 to the minus third, and this is over half a molar. So we're going to end with this much lost, and this is only going to be well, if we go all the way to the end, right, what are we going to have left here? We go all the way down to here, then we're going to use up 2 of those. Right? We're going to use up 2. So 2 times this is what we're going to use up there. So for this one, we're going to have 0.667 minus 2 times 6.67 times 10 to the minus 3. That's what we're going to have left here. And this is going to be MN2 plus. This is going to be that. That's what we're starting with. Let's see. Okay. Three. 2 times that, and subtract that from 0.667. So we've got 6.6, no, 6.54 times 10 to the minus 1 molar here. Now that we've got those values, we should be able to work part of the way back. Wait a minute. That's right. Oh, okay. And we also have to calculate this. Okay, so if we've used up all of this and we formed this, then what do we have over here? Well, what we have over here is that one manganese was over here, and it was this concentration. Right? So now we have this one at our beginning equilibrium position is 6.67 times 10 to the minus 3 molar for this ion. Okay. Okay, so now, if all we want to know is what is this concentration, it's the same up here. We don't have these values to work with. What we have now is this arrangement, and this is what we're looking for right here. Okay, so I'm going to try to squeeze in the ice down here. So this is the initial concentrations. This is I for this calculation. Yeah. That's the initial concentration. We're going to what? We're going to produce some of this. And so this is going to be the change here is going to be plus X there. This is going to be well, we're going to have to take some of that over here, and they're 1 to 1 to 1. So this is minus X, and this is also plus X. Okay, so equilibrium is going to be X here. This is going to be 6.65, excuse me, 6.54 times 10 to the minus 1 plus X. And this is going to be 6.67 times 10 to the minus 3 minus X. Based on this equation. And if we solve for X, we get the value we're looking for. Now, why don't I have X's in here? Okay, yeah, that's right. And that's right. And that's right. 6.67, yeah. Maybe I skipped a step. Yeah, I think I just skipped the X's part. And I just left these X's out so that we could calculate. So what we're going to end up with is our K, this is actually K minus 1 because we took the inverse of it. So K2 equals 79.365, and it's equal to, and I'm just going to drop these X's because their change is not going to be that big. Oh, whoa. No, we're after this one. Aren't we? Isn't that the question? Find the equilibrium concentration of, oh, no, we want the, this is right. Okay, I had it right the first time. So this is going to be this term up here, and we're taking the approximation of 6.67 times 10 to the minus 3. And then in the denominator, we've got the x, and then we've got 6.54 times 10 to the minus 1. Okay, so now I bring x over here, and that's equal to 6.67 times 10 to the minus 3. And this is 79.365, and then 6.54 times 10 to the minus 4. That should give us x. Let's see. I already got that one. 36. So I get x equals 1.29 times 10 to the minus 4, 10 to the minus 4 molar. Did I get even close? Yeah. Yeah, okay. I'm having trouble today, folks. I don't know what it is. Monday. I ate too much ham on Easter. Okay. That looks like a good extra credit problem there. Okay, got about a half hour. Right, 55, 53. What's the molar solubility of lead 2 chromate in 0.055 molar sodium thiosulfate? Oh, okay. This is a formation constant problem. All right. So we've actually got two problems going on here. One is the solubility of of lead chromate. Yeah. This is going to be like the one we were before. Or silver. And then we've got this is, I'm going to put that K over here. KSP is 2 times 10 to the minus 16. Okay. And then the second equation where we form the complex ion, we have thiosulfate with lead. We have lead 2 plus and the thiosulfate. And we need how many of them? 3. And let's see. So that's 6. It should be a -4. Yeah. And the formation constant for this one is 2.2 times 10 to the 6. Okay. All right. Let's see if I've got everything up here correctly. 3. Yep. Now if we add these together, and the question was solubility, wasn't it? Molar solubility of. Okay. Molar solubility here is going to, as this solubilizes, it produces one of those. Because these are going to cancel. We can't base it upon these values right here. Right? Plus 3 S2O3 2 minus. And that then has this one. Oops, no, I canceled that one. Is the chromate. And lead 3 minus aqueous. Okay. Now the K for this equation is going to be that one times that one. Four times 10 to the minus 10, and that's going to be the chromate ion. Right, times complex ion and divided by S2O3 minus cubed. Okay, so far so good. Yep. All right. So initially, we had some of this, right, at 0.055 molar. Yeah, 0.055 molar. And yeah, none of this, none of that. And then the change would be that direction. So if this is going to be our solubility term, this is going to tell us what the solubility is. This should be our S. That means we lost 3 S's on this side because of 1 to 3. And this is also going to produce one of these. So that's S, and this is 0.055 minus 3S. Okay, so the chromate is going to be S. The lead complex ion is going to be S. And this one is going to be 0.055 minus 3s cubed. All right, so this term is going to be s squared is equal to this value right here. Let's see, did I do some estimation? Yeah. I said this is going to be so small that it's not going to matter. So this puts us s squared on top and 0.055 cubed on the bottom. So 0.055 and cube it is 1.66 times 10 to the minus 4. And that's going to be multiplied by this value to put it on this side. And that leaves s squared on that side. So s squared is simply going to be this one times that one. There we go. This is 7.30 times 10 to the minus 14. And then s equals the square root, which is 2.7 times 10 to the minus 7th molar. Okay. I guess this is a multi-step problem. Oh, that was it.